Okay, so let us start. So first of all, it's an incredible honor for me to be introducing Terry. I met Terry in 1997 here. He was a young postdoc, and it was the first time that I was seeing somebody being able to do mathematics sitting in front of a screen that had more brighter colors than my scarf. It was offensive to the eyesight, and he said he was thinking, I believe he was thinking of a Kakeya problem. So I don't understand. I thought, oh, okay, he's a young generation. So I want to point out that Terry is the second Adelaide speaker that we have today. I think has been a while since Adelaide has been so well represented here at MSRI. A bit about Terry, I mean, we've introduced in all of our speakers. So he's a professor at UCLA. He received tenure basically 3 years after receiving his PhD. He was a professor by then. He has received a number of awards. I'm not going to mention them all, but just a couple. The Stalin Prize, the Boucher Prize, the Fields Medal, the MacArthur Prize, and the Breakthrough Prize. He is a fellow of many societies, and he is a member of the National Academy of Sciences. His latest I don't know, I'm going to call it committee work, is the President's Council of Advisors on Science and Technology. And so Terry has also been involved with MSRI, not only as a member, a postdoc, an organizer, but as a member of the Board of Trustees. He is actually the vice chair of the Board of Trustees, and I was relating to another one of our members of the Board of Trustees that we had an important steering committee meeting meeting at the last minute, and Terry had said yes. And then he called and canceled, said, no, I'm really sorry, I cannot be there, and we rescheduled. And of course, he said, my apologies, I have a meeting with the president, I cannot be. So it shows the level of commitment. He told me that's the only reason I will cancel the meeting for MSRI. So I also, I think his talk, the title, says many, many things, but one of the things I don't do much social media, but once in a while I follow some people, and I just want to point out, maybe to put the talk in context, that last weekend Terry wrote, "Today is the first day I could say GPT-4 has saved me a significant amount of tedious work." So I think I'll leave you with that sentence as Terry goes.
So there might be the overflow?
We're okay.
No, okay. Well, you can mention it.
Okay, so I'm supposed to mention that if more people come, there's an overflow room in the second floor in the Baker room where the talk will be projected. Again, I'm sorry, we cannot have people sitting on the stairs. Thank you. Terry?
So, I'm always happy to be back at MSRI. I had so many good memories here. As Tatiana said, I first came here a year after my PhD for a program in harmonic analysis, where I met so many people, including Tatiana, but a lot of my future co-authors. And it really was energizing. I learned a lot about my field and its connections to other areas of mathematics. And I've stayed sort of connected to MSRI ever since in many, many ways. I will not talk about any of my own work here. So I've gotten increasingly interested, kind of actually accidentally, in the role of computers in mathematics. So I was asked to sort of talk maybe more about the future directions of MSRI, future directions of mathematics. And I thought, like, what do I think is the most significant development in the future? And I think it will be the increasing role of computers. So, of course, we all use computers for sort of communicating mathematics. We write using LaTeX, we email our collaborators, we Zoom, and so forth. But largely still, with some small exceptions, we mostly, at least in the pure math side of our subject, we don't use computers so much to create mathematics. Although people do, and I'll give you some historical examples. But this, I think, is changing. I think if pure mathematics currently is maybe sort of 95% humans and 5% computers creating mathematics, the percentages will equalize over the next decade or two, I think. Okay. Some people think they will even flip, but that, I think, is in the far future still. But mathematicians have been using computers for quite a long time. I mean, so if you were to ask, when is the first time computers were used in mathematics? That's kind of a trick question. You might think, 1970, 1950, 1920. It's really the 18th century, actually, because computers were not always electronic. They were first human, and then they were mechanical, and then they were electronic. But computers, for example, the first use of computers were to build log tables and trig tables. They would, there was a profession. Human computers would actually go and perform numerical calculations. Most importantly, at the time, for these tables, people were using computers to simulate, equations or PDEs, for instance, even before the war. For example, in the 1920s, a significant calculation was done by Hendrik Lorentz, so there was a massive dam, I think, or dike or something built in the Netherlands. I cannot pronounce the Afsluit dike. And he wanted to model the effect of it on the fluid flow around the area, so he had to solve a whole bunch of fluid equations, and he got a team of human computers, a cluster of human computers to actually solve this problem. It's noteworthy as one of the first places where he had to actually develop floating point arithmetic, which wasn't the thing then, in order to actually, because there were many, many parameters of very different magnitudes. He had to organize it together. Computers really came into their own during the wars, World War I, but especially World War II. Human computers and mechanical and electronic, the very first electronic computers. Lots and lots of mathematics on ballistics, navigation, the Manhattan Project, all required lots and lots of computational power. In fact, mostly done by actually human computers that were mostly women. Of course, the men were fighting the wars. But in fact, it was so female-dominated. One of the standard units of computing power at the time was the kilogirl hour. How much computation can be done by 1,000 girls with adding machines. That's when large-scale computing started coming into their own. Okay, so how did research mathematicians use computers? So one of the oldest uses, beyond building tables and things, is to make conjectures. One of the famous examples is in the 18th century, when Gauss and Legendre were studying primes, and they were interested in a very basic question: how many primes are there up to a given threshold x? And so they, Gauss at least hired some computers. Actually, Gauss himself was a computer, but I think he also hired some others. And so they created these huge tables of how many primes there were up to, 1 million or so, and started comparing them with various formulas. And so looking at numerical data, for instance, Legendre was one of the first to generate conjectures based on numerical data. So he predicted, so pi of x is the number of primes up to x, so he predicted that pi of x should be asymptotically x over log x minus a constant. This is what he predicted, and this constant became kind of famous. He called it Legendre's constant. Well, he didn't call it that, but it was then called Legendre's constant. But in his writings, he said, based on his numerics, he gave an incredibly precise prediction for what this constant was. Actually, it's not clear how he got so many digits of this prediction, 1.08366, out of only like the numerical data that he had. But this was an influential conjecture. It was later adjusted by Dirichlet to actually a more accurate conjecture. So, of course, what we now learn in textbooks is a slightly different conjecture, not x over log x minus a constant, but actually the logarithmic integral, the integral of log t from 2 to x. And that was proposed by Dirichlet and then finally proven very famously by Hadamard and de Vallée-Poisson in 1896. That's the prime number theorem, the fundamental theorem of analytic number theory. One corollary of that is that Legendre is actually not quite correct. Legendre's constant, which is still called Legendre's constant, actually turns out to be just 1. Euler has his constant E, and Archimedes has his constant pi. So Legendre has claimed 1 as his constant. But anyway, it started a very, very long tradition in analytic number theory of using numerics to make conjectures. Perhaps second to the prime number theory, maybe the second most famous example is the Birchon-Swinton die conjecture, was to a large extent suggested by large numerical evidence. Okay, so that's one sort of classical way in which computation has been used. Another famous historical example, so after the war, they had created all these massive electronic computers, and then the war ended, and they needed to actually justify their use to think of other things to do. So three physicists, Enrico Fermi, Pastor Ulam, and a programmer, Singu. And back then, all the programmers were women, actually. So they decided to use one of the early computers called Maniac to model a one-dimensional crystal. And so it's basically a bunch of particles which repel and attract each other, the neighbors, and in modern language, and actually since, as Dusso explained, pretty much all dynamics you can give in terms of Hamiltonian. So if you have a Hamiltonian, which is the kinetic energy plus a certain amount of potential energy between neighbors, you can create a Hamiltonian. And what they wanted to investigate was the principle of equipartition of energy. So if you had an initial state where only one particle was excited, eventually the energy should transfer itself to other modes, and they expected that eventually that somehow the energy would spread out and every mode should have equal, on average, equal energy. This is the principle of equipartition of energy. But when they actually ran the numerics, which they could for the first time because of this computer, they didn't get that. So they started with an initial state which was concentrated. Yeah, this, I think, is the actual picture from this 1955 paper. Yeah, so they actually, they started with a state whose energy was concentrated on one mode. I think they could do 30 modes, 30 particles. And as they evolved time, the energy state remarkably localized. Only one or two particles had a lot of energy. As far as they could simulate run their simulation, the state remained remarkably coherent. And so, based on this numerics, they were the first to discover at least numerically, the phenomena of solitons. That for certain equations, there are these solitary wave states that say localized and are quite stable. I guess physically they were observed previously. There's a famous story of some British mathematician whose name escapes me riding down a canal, following a soliton for a mile on horseback. But this was numerical evidence of solitons. Although the funny thing is that the numerics weren't. It was only because the numerics were somehow limited. If you run the same experiment on a modern computer, which can go many thousands of times further, you do eventually get decoherence, and the states do actually split up, and equipartition energy actually does happen. We now know what's going on is that this system is actually a discrete approximation to a completely integrable system called the quadratic de Vries equation, and that equation is completely integrable. It does have solitons that stay forever. This one doesn't quite, but it's close enough that with the numerics of the time, they could see this phenomenon. But it was very influential that these modern electronic computers could actually reveal unexpected phenomena. And of course, and now of course it's now commonplace, but that was a big influential development back in the 50s. Now, perhaps the most famous use of computers that you've all heard about, until recently perhaps, is the first major theorem proven using computers, and that was the four-color theorem back in the 70s. So let me just sort of tell you a little bit about how that proof worked. The proof consists of the following things. So first of all, Apple and Haken, who proved the theorem, they gave a list of a certain number of finite graphs, 1,834 finite graphs drawn by hand in their paper, and so consider the following finite family of graphs, okay, which they called configurations. And they proved two statements about this family. Okay, so the first is called reducibility. So that says that suppose you have a graph you want to color, and inside this graph, you have one of those 1,834 finite graphs. Then there's a procedure to take away that graph and replace it with a smaller graph with a property that if you can color this new graph 4 colors, then there's a way to color the original graph with 4 colors. So that this configuration is reducible to the problem of 4 coloring your original graph is reducible to the problem of coloring this smaller graph. Okay, and that they proved basically by computers. So the computers at the time were good enough that for each of these graphs, you could hand code a little program, okay, feed it into the computer, and they would verify that this was actually the case. Then there was the other part is unavoidability, showing that if there was a counterexample to the 4-color theorem, and it was minimal in a certain sense that I won't describe, then any minimal counterexample to the 4-color theorem must contain one of these 1,834 graphs. Once you have both of these 2 facts together, they tell you that there's actually no minimal counterexample because every minimal counterexample had an even smaller counterexample. Now this, technically it was still computer verified, but by a human computer. So the unavoidability is this massive case check analysis, which is actually 400 pages of microfiche, and it was checked by hand by the daughter of one of the authors. So I told you all the human computers were women. That was still the case in the 1970s. So by modern standards, this would not really be considered a computer verifiable proof. And in fact, the list there was numerous tiny errors. The list was not quite, some of the graphs were not quite drawn properly, and it had to be a couple of revisions over the years. It was only in the 90s that a cleaned up proof was produced by Robertson, Sanders, Seymour, and Thomas, using a smaller number of configurations, but more importantly, both the reducibility and unavoidability properties could now be checked fully by an electronic computer. Okay, you didn't need to call up Hacken's daughter again. And in fact, you can go one step further. By 2000s, we also had these formal proof assistants. So these are formal computer languages which give us a very rigid structure type. They encode a very rigid type of proof. That if you want to verify that a certain statement is true, if you can provide a proof in one of these languages, then you can, and it compiles the same way that a LaTeX file will compile if there's no errors. Then it guarantees you that the theorem that you want to prove is true. So there was one of the popular proof assistants called Koch, and it was this theorem was completely formalized in 2005. Okay, so that's one famous example. Another really famous example of computer verified proofs is that of the Kepler conjecture. So Kepler, back in the 17th century, studied sphere packings, so packings of unit spheres in R3, and wanted to know what is the densest way that you can pack spheres in R3. There's sort of a natural packing called the hexagonal close packing, which is drawn here in one of Kepler's original articles, and there's a dual packing called the cubic close packing, and they both have a density of about 74%. They fill up about 74% of space, and the conjecture that this is the right constant, that no other packing, that every other packing attains at most this density. So that was a famous conjecture. It's also very interesting what happens in other dimensions. That's a whole other story, but okay. But in 3 dimensions, this was a famous problem. Now, this is not a problem that you can immediately attack by computer. Like if you only had a finite number of balls and in a finite amount of space, you can imagine that you could solve some finite optimization problem. You just do some calculus or something, just feed it in Mathematica or whatever. But there's infinitely many balls, so you can't directly just try to throw a computer at this. But it was realized early on that in principle, you could reduce this to a finite computation, maybe. So one approach proposed by Toth was that whenever you have a sphere packing, you can build what's called a Voronoi partition. So around every sphere is something called the Voronoi polytope, which is the set of all points that are closer to the center of that sphere than to the center of any other sphere. And that partitions your space into these various polytopes, which are called Voronoi cells. And you can compute their volume. And there's some relationships between these volumes. Like if you have a bunch of Voronoi cells that surround another one, and you know the volumes of each of these cells, it provides some constraints on the volume of these other cells. And Toth made the observation that if you had enough inequalities between these cells, just a finite list of inequalities, you could convert that to some upper bound on the density of a sphere packing. And so in principle, if a computer could produce a good list of inequalities, you could actually maybe attain the sharp upper bound. You can certainly attain some upper bounds on packing with this method. But the question is whether you could attain the sharp bound. So this was a popular attack on this conjecture, and there were many rather high-profile attempts to prove this. Unfortunately, none of them ended up being convincing to the community. Okay, over many years, Thomas Hales worked on this problem, and he decided to work on a much more complicated version of this strategy, where instead of taking the Voronoi partition, he experimented with many other types of polyhedral decompositions, and instead of just computing the volume of each one, he decided to assign a sort of a score to each polyhedral. And what the score was, well, as you see, it was not clear initially exactly what to pick. It was a lot of trial and error. And to prove all these inequalities between these scores, and again, use some sort of linear programming maybe, and convert that into upper bounds on densities. I have a quote. So this method is it's a very flexible method because you get to choose the score, you get to choose the decompositions, but it was maybe too flexible to be feasible. Yeah. So he worked actually with collaborator Samuel Ferguson, and so as you record, like every time he had a problem trying to make the minimization problem work, he could adjust the score to fix the problem, but it would create all these other problems instead. And so every year, the score function became more complicated, but the task became somehow shorter in some sense. But he said it was very unpopular with my colleagues. Every time I presented my work in progress at a conference, I was minimizing a different function. Even worse, the function was mildly incompatible with what I did in earlier papers, and this is why going back and patching the earlier papers. But after about a dozen papers and so forth, they eventually announced in '98 the project was successful, and they were able to derive the Kepler conjecture from a linear programming computation applied to a carefully designed score function, and the linear program involved 150 variables. I think when he started, he was not intending this to be a computer-assisted proof, but he was sort of forced into it by the increasing complexity of the project. The proof consisted, actually, the actual proof consisted of 250 pages of notes and 3 gigabytes of computer programs, data, and results. So they sent it to the Annals, and Annals had really struggled trying to referee this paper. It took 4 years and a panel of 12 referees. The panel was 99% certain of the correctness of the proof, but they could not certify the correctness of the computer calculations. I think now we have more established procedures of how to deal with proofs of large amounts of computer assistance, but this was sort of new territory at the time. Annals eventually accepted the paper. Initially, they had a little caveat about this 99% thing, but I think it's now been removed. So I think they are willing to stand by this as a theorem now. But there was a lot of community doubt about this conjecture, and so Hales actually initiated quite a large project he called a fly spec to completely to write the proof of the Kepler conjecture in a proof-assistant language, like the full-color theorem was, so that you could automatically verify the proof, that you could remove all doubt. Of course, the question, do you trust the proof-assistant compiler? But still, it adds another layer of security to our belief in the proof. He estimated at the time that it would take 20 years. It actually took 11. He had 21 collaborators. The key thing actually is that you don't just sort of take each line of the proof and try to encode it. You have to first write down a human readable blueprint of sort of the main steps of the proof and the logic, but written in a very precise style. So they first produced a blueprint in 2012, and then they were able to formalize it. And so the actual, somehow, the formalized proof actually is quite recent. It only appeared in 2017. Okay. What's next? Oh yeah, so there've been a number of other places where there's been a major central result in the subject, and people are nervous about the validity of the proof. And so, sometimes, as you saw in Dussel's talk, you can try to rewrite it and to make it more human accessible. But we now have this other option of just trying to formally verify it. Perhaps the most famous one in recent years is Peter Schultz's liquid tensor experiment. So this involves mathematics I don't understand, but it involves an area of mathematics which Schultz largely invented called condensed mathematics, which is an attempt to repair some of the, there are categories of various important spaces like topological abelian groups, which are used all the time across mathematics, but unfortunately they're not great categories. They're not, so despite the name, the category of topological abelian groups is not an abelian category. And there's a bunch of other things which that are not so great about this category, which I'm not an expert on. But he realized that you could fix a lot of the problems with these categories by replacing these categories by a more sophisticated notion, which are called condensed spaces. For example, you replace topological abelian groups by condensed abelian groups. I am not qualified to explain exactly what a condensed space is, but very roughly speaking, instead of looking at the points of a space individually, you look at how totally disconnected sets, like Cantor sets, map into your space, and how they relate to each other, and this somehow fixes a lot of these problems. Okay, but anyway, he wanted to apply this theory to Banach spaces, and so that his hope was to turn functional analysis from analysis into algebra, which, okay, well, he's entitled to do that. Yeah, so so he was able to get a satisfactory theory, but there was he needed a certain X group to vanish. Okay, okay, so I will not define any of the terms in this equation, but okay, yeah, so there's oh yeah, so every P Banach space and every proof finite set, you take a certain set of measures on the space, and you take a certain X functor on the category of condensed abelian groups, and something has to vanish. Okay, but all right, and so this was a fundamental result that Clausen and Schultz established, and they needed it to do anything in condensed Banach spaces. So he wrote a blog post in 2020 where he talked about how hard it was to prove this theorem. He spent a whole year obsessed with this proof, getting crazy over it. In the end, we were able to get an argument pinned down on paper, but no one else has dared look at the details of this, and so I have some small lingering doubts. With this theorem, the condensed formalism, the hope that the condensed formalism can be fruitfully applied to real function analysis stands or falls. I think this theorem is of the utmost foundational importance, so being 99% sure is not enough. While I was very happy to see many study groups on condensed mathematics throughout the world, to my knowledge, all of them have stopped short of this proof. Yes, this proof is not much fun. I think this may be my most important theorem to date, which is really saying something. Better be sure it's correct. So he was very motivated to find some way to validate this proof. And so he proposed what he called the liquid tensor experiment to formalize this in a modern proof system called lean. And part of the problem was that most of the fields of mathematics that he needed were not in the library. So lean had library routines for real numbers and calculus. I think they had Banach spaces, but things like homological algebra, Sheaf's theory, topos theory were just mostly absent. So part of the task of this experiment was actually just to fill in the library and actually have formal proofs of all the basic fundamental results in these areas. And so within a year, they managed to validate a key sub-theorem, and then a year afterwards, they could get a full proof. It was a big group led by Comlin and Topaz, and Schultz was consulted very, very frequently in this process. In the course of this proof, they found a couple of really small typos and things in the original argument, which they fixed, and they found a number of simplifications. They also found a rather big simplification. So this is, again, these are words I don't really understand, but the original proof used something called the Breen-Deligne resolution. I think it's in homological algebra, which was, but it required, to actually use this, required verifying a lot of difficult axioms. But this was hard to formalize, so they actually decided to formalize something weaker, which was easier to, the axioms were weaker, easier to verify, but that was still good enough for this particular project. And actually, it led to the realization that actually the full Green-Delisle resolution is not needed for many other similar applications. But maybe one of the main values of this project is that it made the Lean's math library a lot more complete. And actually, so like further projects to formalize in Lean have become a lot easier because of all the library routines that have been built in part by this project. As with FlySpec, as with Hale's project, the key thing is to first write a blueprint, a human-readable version of the proof, which you can then step by step try to formalize. One nice thing about this blueprint, you can see it's on the web. It actually gives a very nice interactive proof of the whole thing. You know, a normal LaTeX proof is a static document. You know, it's just a bunch of pages of a PDF. But you know, you can have a proof, and you know, you can say you may give a short explanation. You know, by so and so this follows, but you can click to expand it, and it'll give a larger, a longer explanation, and you can keep expanding quite a bit. So you know, it's a much more sort of clean and modern way to navigate through proofs. And so one nice byproduct of this formalization procedure is that not only does it make it easier for computers to verify this theorem, but also humans. In fact, inspired by this, there's now been work, I'm sorry that the resolution here is not as good as I thought, there's now software that can take, it can't take every single Lean proof, but there are certain families of Lean proofs where there's now automated software that you can take this formal proof, which is not super readable to anyone who's not expert in Lean, but you can convert it into an interactive proof which looks fairly like standard mathematical English. So here is a theorem which was proven in Lean. It's a topological theorem. It's just that if you have I think a map from one topological space to a regular topological space, which is continuous at every point, it's continuous within a dense set, then it's actually continuous everywhere. It's actually continuous, and it provides a proof. And again, the proof, you can expand and contract various parts of it. You can, at any point in the proof, it will tell you what the running standing hypotheses are of the proof and what you're trying to prove. And you know, you can navigate to it. And so, you know, one can imagine, you know, in the future, like topology textbooks, you know, might have things like this. There'll be interactive things where you can just step through one bit by bit, and if there's ever a step which is unclear, you expand it into simpler things, and maybe all the way down to axioms if you need to. Okay. So that's one. I think that's one very promising way in which computer assistance is becoming used in mathematics is to increasingly the increasingly more formal proofs. Then there's just the other sort of more common thing maybe is just using computers to do brute force computation. So sometimes there are these massive computations that the path of least resistance is just to throw a big computer at it. So for example, the odd-Goldbach conjecture, every odd number bigger than 9 is the sum of 3 primes. This was proved by Helfgott in 2013. And so it consists of the proof consists of two things. So one is a human-readable monograph, which is about 500 pages long, using various inequalities, analytic number theory type inequalities. He took care to actually computer verify quite a few of these inequalities. And the upshot of the monograph is that he shows that every number bigger than 10 to the 30, every odd number bigger than 10 to the 30 is the sum of 3 primes. In addition to verifying inequality, it also needs quite a bit of numerical verification of the generalized Riemann hypothesis, which was done in a separate computation. But then you also have to just verify that all the numbers less than 10 to the 30 were also sum of 3 primes. And this was basically just done by computer. A little bit of clever optimization, but not much. So that's sort of a standard kind of brute force use of mathematics, of computers, sorry. One I'm kind of fond of is that in 2016, there was this Ramsey theoretic problem. there's this thing called the Boolean Pythagorean triples problem. So Pythagorean triple is a number is a triple ABC such of integers, natural numbers, such as a squared plus b squared equals c squared. And there's this problem, if you two-color the natural numbers, if you color them in two colors, can you find somewhere in that in one of the two color classes, can you find a Pythagorean triple which is monochromatic, they're all the same color? So this is a class of results called Ramsey type results. And it was not known whether this was actually possible, whether this was actually true or not. If it was true, there must be some finite threshold at which it becomes true. And it was actually computed by computer what the threshold was. So if you color the numbers from 1 to 7824, there's a two coloring that avoids all monochromatic progressions. But if you go to 7825, no matter which of these two coloring you pick, and there's 2 to the 7825 of those, it's quite a lot. But no matter which ones you pick, there must be a Pythagorean triple of all the same color. So this is actually a really massive 3-sat problem, if you know what 3-sat is. And so this was basically proven. Well, okay, it wasn't just throwing off-the-shelf 3-sat solver at this problem. They had to really customize the 3-sat solvability technology to solve this problem. But they were able to do this. It ran for 4 CPU years on a supercomputer, but they parallelized it, so it took less than 4 years. And it produced a proof certificate, which was originally 200 terabytes. This, at the time, it claimed the record for the world's longest proof. Although it can be compressed to a mere 68 gigabytes if you wish. Okay, although it no longer holds the record because a year later, Martin Euler also proved a similar theorem for 5161, and that proof is 2 petabytes in length. Anyway, so that is, of course, another way in which computers get used as sort of brute force calculation. For a long time, I kind of thought, in one of my areas of research, PDEs, it wouldn't be, the computers would not play a major role. But even in sort of my field where things are infinite dimensional and stuff like that, and you don't obviously see sort of the role of finite computations, except maybe to do numerical experiments, like we saw with the Fermi-Pasti-Ulam Singu experiment. But it can actually also prove rigorous mathematics. Okay, so one of the maybe the second most notorious open problem in fluid equations is to show finite time blow-up for the incompressible Euler equations. The first most infamous is the finite time blow-up for the Navier-Stokes, which is a cousin of Euler. But we've been able to make progress on this problem. There were numerical simulations almost 10 years ago that suggested there were solutions that looked like they were developing singularities, that they started off smooth, but they became more and more turbulent and were beginning to focus at the energy in individual points. But these numerics had only finite level accuracy, and the numerics were not reliable long before you actually reached the singularity. So they were not conclusive. But it was realized eventually that if you could find a solution, so one way to construct a solution to a fluid equation that blows up in finite time is to create one which is self-similar, that after a certain point is a rescaled version of what you started with, and then that one will evolve to a rescaled version of itself. And so people have been hunting for these self-similar solutions for quite a while. It's a little bit like these closed geodesics closed trajectories in Dueser's talk. But one thing I was realized is that if you could use computers to maybe find an approximate self-similar solution, one that almost came back to a rescaled version of itself, plus a tiny error. And if you could couple that with a rigorous stability analysis of what happens to perturbations around that that approximate self-similar solution, you could actually rigorously prove an actual self-similar solution blow up. So this became a dream. And there were 2 attempts to do this in just last year. So one was, the first attempt actually was maybe a very novel use, not just of just trying to numerically solve these equations, but actually to use neural networks. Okay, something called a physics-informed neural network that sort of learned from many examples of other solutions to the same equation, and then try to produce solutions of their own, but still compliant with the laws of physics, like the conservation of energy and so forth. and they were able to construct an approximate solution that looked like it was so similar, but they couldn't do the stability analysis. But it was still one of the first times where we could see the power of these modern networks to actually produce these things. But then actually a different group of authors produced another discretely self-similar solution using a more traditional numerical solver. And that one they were able to get, do a stability analysis and actually get a rigorous proof of blow-up for finite incompressible Euler. Okay, well, one caveat, they needed a boundary. It's not quite in free space, which is still a major open problem. And so these are quite influential works, and so now people are doing all kinds of things to find other ways to find blow-up for fluid equations. Of course, the biggest prize is the Navier-Stokes blow-up, which, for various technical reasons, this strategy doesn't work. Navier-Stokes doesn't actually have the discretely self-similar solutions of the type that would work here. But it's not hopeless, actually. Proving regularity, I think, is hopeless. But demonstrating blow-up, I think that there is actually a chance, and we might see it, progress on that in the next few years. Okay, so now another example, recent example of how modern computer systems have been used is in knot theory. So I'm very glad to have Ian have introduced this topic because it actually connects quite a bit. So as we've seen, people care a lot about knots and all their various invariants. And so as we've seen in the previous talk, given a knot, you can construct all kinds of interesting invariants attached to it. So there's the Jones polynomial and the Humphrey polynomial, as we saw. There's also these hyperbolic invariants. So many knots are hyperbolic knots. And so the boundary, their complement is a hyperbolic space, and you can compute their volume. And a couple of other, there's a couple other statistics that you can compute for any given hyperbolic knot. And it's just a bunch of real and complex numbers. The volume, the cusp shape, and so forth. But then there's also like topological things. So there's something called the signature, which is defined more topologically. So instead of looking at the knot complement, you take a knot, you view it as a boundary of a surface, it's called a Seifert surface. And there's an intersection form called the Seifert form, and that's a bilinear form, and the signature of that is some integer. So there's also a signature that shows up. And so a group of authors, I think, Davies, Juhas, Lackenby, and Tomasev, were interested in seeing if there was any connection between the hyperbolic invariants and the signature. So I guess there's one more Spider-Man in Ian's picture there. And so they had a novel way to attack this problem. So what they did was that, so they generated a database of about 2 million knots. And for each of the 2 million hyperbolic knots. And for each of these knots, they computed about 20 different hyperbolic invariants, hyperbolic volume and a whole bunch of other things. And they also computed the signature. And they just took a neural net and said, okay, train on this. Okay, so given all this data, try to interpolate between all this data. And basically, so you can think of this data as sort of a bunch of data points as a partially defined function from R to the 20 to the integers. So there's 20 hyperbolic. Actually, for complex numbers, you have to, some of the invariants are complex, you need to split in real and imaginary parts, but 20 real or complex numbers mapping to an integer, try to fit all your data and find a function that interpolates or almost interpolates this. And so that's what neural nets do. Okay, so neural nets basically interpolate lots and lots of data. And after training, they found that the neural net could produce a function which, if they fed it a new knot, which it hadn't seen before, and it gave it the 20 hyperbolic invariants, it could predict the signature with high accuracy. I don't know the actual percentages, but something like 90%. It got the signature right. So what this showed was that there must be a connection. That the hyperbolic invariants somehow encoded either the signature or a large part of the signature. But the problem with neural nets is that while it does produce a function that interpolates, this function is insanely complicated. It's not like a simple formula that you can just inspect and say, oh, clearly it's a linear or quadratic relationship or something. It's this nasty nonlinear thing. So it's basically this black box, but it's not completely black. I mean, the neural net is made up of these little neurons, and it's a composition of like hundreds and hundreds of elementary functions just composed together in a nonlinear way. But then you can do things with that. So, for example, one basic thing you can do, once you have this black box function that takes in 20 real numbers as input and spits out an integer's output, you can do what's called a saliency analysis. You can take one of your 20 inputs and just jiggle it a little bit, basically just differentiate, do a partial derivative, and see to what extent varying one of the inputs changes the output. And what you hope is that some inputs are very important, and they will change a lot. They will be the integer output is very sensitive to that input, and some are not very important at all. And so there's a way to do that. It's called saliency analysis. And so they took all the 20 inputs, and when they did the saliency analysis, they found that there were 3 inputs that were really important, that they really controlled the output, and all the other ones were not very important at all. And the 3 that were important were a surprise. Okay, it's the real and complex parts of what's called meridional translation and something called longitudinal translation. We'll not define these at all. But there were 3 numbers that were not expected to be the most important features of this knot. But the neural net thought they were really important. But see, once you have those 3, you can just forget all the other inputs, and you can start doing like scatter plots. Okay, well you have 3 inputs and 1 output, so that's 4 dimensions. So but you know, with the assistance of color and so forth, you can start scatter plotting the signature against these invariants, and you have these 2 million data points, and you start seeing patterns. You know, so you get scatter points that clearly sort of fit on some surface, and you can start visually making conjectures. So the neural net provided a really big clue, and then following the clue, they were able to make a conjecture connecting the signature to these various inputs. Now, it turns out that their first conjecture was actually incorrect, and some further numerics disproved the conjecture they had. This is another thing when the conjectures that computers provide you often, they're not quite correct. You know, you saw with Legendre, even Legendre's conjecture wasn't quite correct. But it was close enough that with a bit more work, they were able to fix the conjecture to a better conjecture. And actually, that one they were actually able to prove. So once they had the right form of the conjecture, then they could see what was needed, what type of tools were needed to actually prove it, and then that the proof actually worked. So they were actually able to get a rigorous inequality connecting signature with a bunch of hypothetical invariants. So this is kind of the state of the art of how computers and human mathematicians interact. You know, it's not just like you can give the problem to a computer and the computer solves it. The computer gives you clues, and it's not completely accurate sometimes, but it really helps you, can really guide you in the right direction. But the human still needs to check it and take the next step and do the high-level planning. There are many. I mean, I could go on for quite. I mean, there's no way I can summarize every single way that computers can be used. But I mentioned one way which lots of people. I mean, it's sort of we take it for granted now. But you know, every time we have a problem and some sequence of integers gets produced by our problem, for most of us, we are trained now that the first thing we should do is that we should go look up the online encyclopedia of integer sequences and see if the sequence of numbers that has shown up in your problem has also shown up in some other context. And this is, you know, this can save a lot of time. I mean, it's personally for me, like often I had to figure out how many ways can you do something with endpoints or something, and rather than do the combinatorics or look up Stanley's book, it's just easier to work out the first 5 numbers, plug in the OIS, and say, this was the modified Catalan number or something. Okay, but yeah, so that's the most famous example of what you might call a fingerprint database. So for a given piece of mathematics, if it generates an integer sequence, that's a fingerprint of that result, and 2 theorems with the same fingerprint have a chance to be connected. The most famous example, I think, is monstrous moonshine, where something coefficients of the J invariant and some representation theory numbers produce the same integer sequence, which was a big clue of something really important. I think that was not discovered through the OAIS. It was discovered manually. But I think there are countless examples of other connections that were discovered first through OAIS. There are attempts to make other fingerprint databases. There are some databases of interesting real numbers. What I would love is a database where if you prove an interesting lemma in one field and you think there's another lemma, that this lemma has been proven before but maybe in a different field, is there some way to do a semantic search and say that this lemma you're proving was also proven in this paper from 1970 in a completely different subject in Russian. Yeah, this technology doesn't quite exist yet, although the latest GPT things. They sometimes do make unexpected connections, but it's still, I think we don't have the technology yet. Right. Okay. So the most recent development and very high profile is the advent of these large language models, which are basically very advanced algorithms where given a string of text, just predict the next word in the text, to, autocomplete basically, and then you just autocomplete. And for many years this was like considered a toy. If you take a chatbot from like 10 years ago and you just or if you take your phone and you just keep auto-completing a sentence, you get something which is sort of locally English, but sort of globally it makes no sense. But the technology has gone a lot better. There are ways for text these auto-completers to retain memory of the structure of your text. And they can now do quite amazing things. Okay, maybe many of you have maybe tried to plug in a math question or something into GPT, and sometimes if it's a simple enough question, it will give you the right answer. Sometimes it will give you nonsense. Sometimes it can do quite amazing things. So this is from a recent paper. One of the most advanced models, GPT-4, someone fed it a problem from the most recent math Olympiad. If a continuous smooth function such for every x there's a y, such that g of x plus g of y is less than 2xy, prove that g of x is x squared. It's a non-trivial function, and this is a problem that appeared after the cutoff date. So this model was trained on everything on the internet up to 2021, and then this problem came out in 2022. So it did know about this problem, and it was actually able to write a correct proof of this problem. Now, this is cherry picking. So I think the success rate of GPT on IMO problems is about 1% currently. But this is proof of concept that these models actually are doing something. Yeah. In general, I think they're kind of at the level right now of a somewhat confused undergraduate who doesn't really understand the material but has studied everything. But the technology is still improving. But I should say that so this is impressive because of an IMO problem, but it still has many basic flaws. For example, it struggles with arithmetic. So in a very similar, the same authors actually, they asked it to solve a simple equation, 7 times 4 is 8 times 8, and it instantly said, oh, it's 120. But then it paused a little bit and said, okay, and here's why it's 120. It says, okay, you expand this out, you do this, you put in parentheses, you work out each step by step, and it actually arrives at the correct answer, which is 92. But the very first thing, you see, again, what these things do is that they take your sentence and they just complete what is the most likely next token, the next word that would appear after this. And they decided that the most likely next thing is 120. But then the most likely thing after that is to explain why 120. And so they gave the explanation. And by following the explanation and just auto-completing, they arrived at 92, which is the correct answer. Okay, and so they asked, okay, but wait, you started by saying 120, and they say, oh, that was a typo. Sorry, the correct answer is 92. So the reliability of these tools is an ongoing problem, but I think this will improve over time. Yeah, so there's lots of interesting experiments now. So right now, like the GPTs that you see on OpenAI or whatever, they're just pure autocomplete. Right? They're not actually computing anything. Like they have no inbuilt calculation machine. They do not know 7 times 4 is 28. It's just that in their training, they've seen that the most natural autocomplete of 7 times 4 equals is 28, and they use that information. So it's like they've memorized lots and lots of tables and so forth. But they've now figured out how to connect GPT with plugins. So like there's a recent development where they can plug in Wolfram Alpha. And so every time GPT is faced with a math problem and it's of a type that they know that they can solve by Wolfram, they just farm it out to Wolfram, and Wolfram will do the calculation for it. And there's lots of other experiments. There's one interesting one where you try to train a GPT to produce lean code. And then you run it through a lean compiler, and if it doesn't compile, it will feed back the error message, and then it has to fix it. And until finally it actually generates actual lean code. And it can now, you can take very short, small steps in a proof, from one line to the next, clearly, if this is true, then this is true, and it can expand them out into a piece of lean code. So in the future, I think we'll start seeing AI-assisted formal proof verification. It will be a development. I think also just, if you've ever played with these things, they're like a colleague who's infinitely patient and will listen to you, and you can bounce crazy ideas off of it, and it won't judge you. And actually, that's kind of valuable. So I mean, I've talked to these models about math. It hasn't yet actually come up with really impressive. It's just I would say things. Oh, have you tried looking for counterexamples? Have you? But every so often, have you tried looking at the work of this author? Okay, and it's an author which is actually in an adjacent field. And again, sort of autocomplete. I think it's just coming up with it, but it's sort of relevant sometimes. And I think I asked it once a question to bound the rate of decay of you take a sum of n random variables, and you ask how fast the tail probabilities diverge. And what I was looking for, I was wondering if GPT knew about something called Cramer's theorem, which is actually a rule that predicts the precise large deviation rate for the sum of independent random variables. But I didn't use the word Cramer's theorem or large deviations. I gave the request in plain English, well, in using other mathematical terms, and it gave a somewhat nonsense answer. But it mentioned the logarithmic moment generating function as part of its answer, which is actually so. Cramer's theorem says that the rate function for some n independent variables is the Legendre transform of the logarithmic moment generating function. So it somehow knew through all the various connections in its neural network that this was a relevant concept. I didn't mention it, but it didn't know how to put it together and give a coherent response to my question. So it has some intuition, but it can't sort of actualize it sometimes. But I think in the future, we will start seeing more and more uses of this as inspiration or just to suggest interesting approaches. Yeah, so where are we at? We're not yet at this, so with this one Olympiad problem aside, we're not yet at the point where we can just plug in, please solve the Riemann hypothesis for me or whatever. Okay, and it will. Well, you can try. It will spit out a bunch of plausible sounding nonsense. But I think they're increasingly very useful as assistants. I mean, not just as brute force computation tools, but to suggest all kinds of interesting leads and clues, and just as someone as a partner to bounce ideas off of. They're beginning to be useful at generating conjectures or making connections that you wouldn't normally see. So it's at the cusp. I think we're going to see a lot more interesting mathematics generated with really non-trivial new uses of computers. And not just, and while also it's going to help us not just in our core task of proving theorems and making conjectures, but it really helps us in all other areas as well. Just for example, this talk actually, one of the ways I prepared for this talk is actually to ask GPT what are some about the history of where computers were used, and so actually it gave some suggestions which I incorporated into the talk. I encourage you to play with these tools. They're non-trivial. It's sort of unintuitive. Like for example, most computer tools we're used to are very, very fussy. Like LaTeX, for example. Like if you type in some LaTeX and you get the parentheses wrong or something, it will complain endlessly. But these tools, you can give very vague input. In fact, the vaguer the better somehow. Okay, and you can still get very structured, interesting answers. I think we have just scratching the surface of the power of these tools. Okay, I think that's it. So thank you very much.